Assalamualaikum and salam sejahtera. Today will be our last topic 7, on accuracy assessment in remotely sensed categorical information. Okay, we will discuss on why we bother for accuracy assessment and what is accuracy assessment, how to perform accuracy assessment. The key points is to construct confusion matrix and then to compute accuracy measures. But the difficult points is statistic for sampling designs and special analysis. Why do we bother accuracy assessment? Thematic maps of land cover, forest types, and others can be derived from classifications of remotely sensed imagery in combination with ancillary data sets. You need to tell map users how well it actually represents what's out there. So without an accuracy assessment, a classified map is just a pretty picture. The accuracy of information derived from remotely sensed image will always be asked. Sometimes it's very difficult to address. Accuracy of a map or image can be evaluated or identified. Accuracy defines correctness. It measures the agreement between a standard assumed to be correct and classified image of unknown quality. If the image classification corresponds closely with the standard, it is said to be accurate. The accuracy assessment task can be defined as one of comparing two maps. One based upon analysis of remotely sensed data, the map to be evaluated, and another upon a different source of information. The second map is the reference map, assumed to be accurate, that forms the standard for comparison. Okay, what is accuracy assessment? To assess how well a classifier works, and then to interpret the usefulness of someone else's classifications. How do we do accuracy assessment? Okay, first, collect reference data, for example, ground truth, and then determining class types at specific locations. Compare a map with the reference to compute accuracy measures, and then interpretation of the results. Okay, the reference data can be any possible sources, either area photo interpretation, ground truthing with GPS, or GIS layers. But make sure we can actually extract from the reference source the information needed. For discriminating 4 species of grass, for example, we may need ground surveys, not aerial photographs. So aerial photograph is not possible for you to differentiate 4 species of grass. Determining a size of reference plots, match a spatial scale of reference plot and remotely sensed data. For the ground plots, 5 meter on a site may not be useful for remotely sensed imagery. May need aerial photograph or even other satellite imagery. Okay, to take into account special frequencies of image, we need to consider photo reference plots that cover an area 3 pixels on a site. Example 1, low spatial frequency, homogeneous. Example 2, high spatial frequency, heterogeneous. So, low spatial frequency, homogeneous, two classes here. But for heterogeneous, we have 3 classes here. Implication for position accuracy is consider the situation where the position of the image is plus or minus in 1 pixels. This is example 1 for low spatial frequency, and then example 2, high spatial frequency. Okay, to determining a number and position of sample, first to make sure that the sample is adequately landscape. And then must have a variety of sample schemes. For example, random, stratified random, static, and etc. The more reference plots, the better you can estimate how many you need statistically. In reality, you can never get enough. Let's say in Lil Sun and Kiefer studies, this suggests 50 uh, samples per class as rule of thumb. Okay, this is a sample size calculation. Fitzpatrick Lin's 1981 suggests that the sample size n to be used to assess the accuracy of a land use classification map be determined from the formula for the binomial probability theory as shown here, which is n equal to z square p q and divided to e squared, where p is the expected percent accuracy of the entire map, q is equal to 100 minus p, e is the allowable error, and z is equal to 2 for the 95% two-sided confidence level. Okay, for a sample for which the expected accuracy is 85% at an allowable error of 5%. For example, it is 95% accurate. The number of points necessary for reliable result is 203 points. So this is the error, possible allowable error, 5%. So the number of samples we need is 203. The acceptable error of 10%. So the sample size for a map would be 51 points. Okay, sampling approach to reduce analyst bias. We have three sampling approach. First is sample random sampling. Every pixels has equal chance. And then a stratified random sampling. Number of points will be number of samples points will be stratified to the distribution of thematic layer classes. The larger classes, the more points needed. And then equalize a random sampling. Each classes will have equal number of random points. Let's say a sample size at least 30 samples per land cover class. Okay, simple random sampling. Observation are randomly placed on the entire of the classification map. For stratified sampling, we have two: systematic sampling. Observation are placed at equal interval according to a strategy. And then a systematic non-aligned sampling, a grid provides even distribution of randomly placed observation. So each grid has equal number of samples. Okay, the third one is cluster sampling. Randomly placed centroids used as a base for of several nearby observations, which can be selected randomly or systematically. Okay, the error matrix. The standard form for reporting site-specific error is the error matrix, sometimes referred to as the confusion matrix. It identifies not only overall errors for each category, but also misclassification due to confusion between categories by category. Tomlinson, 1999, set a target of an overall accuracy of 85% with no class less than 70% accurate. So kita tengok accuracy assessment on the total accuracy. Number of correct plots divided to total number of plots. Okay, kalau kita tengok sini ada dua classified maps. number of samples for classified map, and then a reference map or reference source. Okay, for example, we have three classes here: conifer, hardwood, and water. Okay, 50 samples is correct on a classified map and reference source. And then 13 also correct number of lots that correctly classified. Sama juga dengan water. So 71 bahagi dengan 100 darab dengan 100, lalu dapat dia punya percentage dia adalah 71% accurate. But we have a problem with total accuracy. Kalau kita rely on the total accuracy sahaja, summary value is an average, which does not reveal if error was evenly distributed between classes, or if some classes were really bad or some really good. Therefore, it must be included other forms. The first is users accuracy, and then second one is producers accuracy. So kita di samping daripada total accuracy tadi, kita kena tengok juga daripada users accuracy and producers accuracy. Dan some classes has really bad or some really good. Okay, from the perspective of the user of the classified map, how accurate is the map? For a given class, how many of the pixels on the map are actually what they say they are? It can be calculated as number correctly identified in a given map class divided to number claimed to be in that map class. Maksudnya, berapa yang betul, yang sepatutnya bahagi dengan berapa yang user dah set. Contohnya, kalau ada kelas water, ada sampel ada 10, 5 betul. So 5 yang betul, number correctly identified in a given map class, sama dengan reference map. And then 10 adalah jumlah yang dalam classified map tersebut. So kalau kita nak tengok macam mana kita nak kira user accuracy tu, okay, ada dalam ni class types determined from classified map. Conifer ni, kelas conifer yang betul 50. Maksud dia sama dengan reference source dia 50. Okay. Jumlah yang untuk kelas conifer ni kat dalam classified map ni ada 57. So 50 betul bagi dengan 50 dapat dengan 1, kita dapat dia punya user accuracy untuk conifer adalah 88%. Okay. Kemudian kita tengok producers accuracy pula. The perspective of the maker of the classified map, how accurate is the map? For a given class in reference plots, how many of the pixels on the map are labeled correctly? So we calculated as number correctly identified in reference plots of a given class divided to number actually in that reference class. So kalau kita tengok yang ni, so, total number yang betul sama dengan classified map, sama dengan reference source. Tapi total of reference source untuk conifer ni sahaja, untuk conifer ni sahaja 50, 14 dengan 3. So total dia 67. 67 sampel tu ada dekat dalam conifer. Tapi 50 yang tu reference source ni dengan 100 sama dengan 75%. So kalau kita tengok tadi yang user accuracy 88%. Tapi kalau kita daripada perspektif of producer tadi, dia 75%. Okay, so ini dia punya summary untuk dapatkan dia punya overall accuracy based on total accuracy tadi dengan user accuracy dengan producers accuracy. So untuk conifer tadi, kalau dekat dalam producer accuracy 75%, tapi dekat hardwood, untuk hardwood dia rendah, accuracy dia 57%. Water tinggi 67. Sama jugalah dengan users accuracy, conifer dengan water, conifer tinggi, hardwood dengan water agak rendah. So kita tengok pula dia punya Kappa statistics. Kita nak tengok tadi kita dah kata dia sebab first tadi kita tengok yang first dia punya accuracy dia tadi total accuracy dia ni 71%. Total accuracy ni 71%. Lepas tu kita tengok users accuracy untuk setiap classes dan kita tengok producers accuracy untuk setiap classes juga. Tapi kita nak tengok dia punya statistik ketepatan dia dengan nilai sebenar. So kita tengok dia punya Kappa statistik. That estimated SK Kappa. Nak tengok dia punya perbezaan antara actual agreement and the agreement expected by chances. Yang kita expect, yang kita hasilkan map dengan yang nilai sebenar sepatutnya, reference source tadi. So Kappa of 0.85 means there is 85% better agreement than by chance loan. So maksudnya kalau nilai Kappa tu mengambil satu lebih tinggi 0.85, so dia punya accuracy dia 85% better. Okay, kalau tadi kita tengok on accuracy of total correctness tadi, kita tengok pula error of omission and then error of commission. Kalau error of omission ni on the perspective of policy accuracy lah tadi, iaitu reference source tadi. Okay. Error of omission ni pixels in class 1 erroneously assigned to class 2. From the class 1 perspective, these pixels should have been classified as class 1 but were omitted. Okay, dia sepatutnya adalah kelas 1 tapi dia dikelaskan sebagai kelas 2. Okay. Dalam reference source tadi dia kelas 1. Sepatutnya lah point tersebut dekat dalam sampel tu. Tapi dekat dalam classified map dia adalah kelas 2. Sepatutnya dia kelas 1. So dia dah tertinggal lah, dia dah tak termasuk dalam producers accuracy tadi. So bila dia tak termasuk dalam producers accuracy tadi, dia adalah error of omission. Okay, so error of commission ni pixel in class 2 erroneously assigned to class 1. Okay, from the class 1 perspective, this pixel should not have been classified as class but were included. Dia sepatutnya dia adalah kelas 2. Dekat dalam reference map, reference source dia adalah kelas 2. Tetapi dekat dalam classified map dia adalah kelas 1. So dia dah dari segi perspektif kelas 1 ni tadi, dia tak sepatutnya adalah kelas 1, dia sepatutnya ada kelas 2. So sama jugalah dengan user, sama macam producer accuracy. Kalau users accuracy dia tadi, 88%, 88%, so 12% dia adalah error of commission yang tak termasuk sekali dengan dalam users accuracy tadi. Ini contoh dalam bentuk graf lah. So error of omission versus commission from a class 2 perspective. Jadi error. So ini adalah error of omission. Yang ini adalah commission error. Omission ni tadi dekat dalam reference source tadi. So, yang dekat dalam reference source, kalau ada 10 reference source, 8 betul, sama. Lagi another tu tak sama. So ini adalah error of omission. Kalau error of commission tadi sepatutnya dia adalah kelas 1 tapi dia assign dalam kelas 2 tadi. Kelas 1 assign kelas. So ini adalah error of commission. Okay, kita tengok Kappa coefficient. Provides a difference measurement between the observed agreement of two maps and agreement that is contributed by chance alone. A Kappa coefficient of 90% may be interpreted as 90% beta classification, then would be expected by random assignment of classes. Okay, what's a good Kappa? Okay, general range, less than 0.4 value is poor. Okay, between 0.4 to 0.75 is good, and above 0.75 is excellent. Allows for statistical comparison between metrics, useful in comparing different classification approach to objectively decide which give best results. Okay, this is the formula of Kappa coefficients. Okay, we have a sum across all rows in matrix, diagonal, marginal row total, and marginal column total, and number of observation tadilah. Okay, this is the example. And then this also the example of accuracy assessment measures. Okay, for the interpreting result of accuracy assessment can be fact, misclassification in remotely sensed data, di mana classes are land use, not land cover, classes not spectrally separable, special scale of remote sensing instrument does not match classification scheme, and error in reference data is subjectivity and interpreter error. How to improving the classification accuracy? Can use a land use or land cover with incorporate other data, and then spectral inseparability, hyperspectral multiple dates, and then scale using a different sensor, aggregate the pixels, and then classifiers use hierarchical classification scheme, and then in maximum likelihood classification use prior probabilities to with minority classes more. Okay, so added value to remote sensing and information products and to ensure their proper use. Ground truth is itself difficult to acquire, especially for the large area. And then sampling design is important for cost effectiveness in accuracy assessment. Accuracy assessment as an integral component in the information process. Okay, this is the reference listed for this topic. Okay, that's all for this topic. Thank you.